So, a federal law requires periodic testing in standard subjects. A random sample of 52 junior high school students from Oceanside was selected, and each student's score on a standardized mathematics exam and a standardized English exam were recorded. School administrators were interested in the relationship between the two scores. Suppose the correlation coefficient for the two exam scores is 0.84. Use alpha of 0.01 where needed. So first thing I want to make sure we know, what is the sample correlation coefficient, or the lowercase r? Yep, the r is the 0.84. So you can see here in this sentence, suppose the correlation coefficient for the two exam scores is 0.84. So that was our clue right here, the word correlation coefficient. It didn't say sample, but because it talks about the two exam scores from the sample, it's implied. So that's where we get our R from. And then based on this number, 0.84, how would you describe the correlation? Is it positive or negative? Yep, it's positive. And would you describe it as strong or weak? And remember, the closer it is to 1 or -1, the stronger it is. The closer it is to 0, the weaker it is. Yep, this would be considered strong. So in general, an R that's like 0.7 and up, or -0.7 and more, so -0.8, -0.9, those are considered strong because they're closer to the -1 and 1. Moderately is like 0.5 to 0.7, and weak is anything between -0.5 and 0.5. So I know it's hard to imagine it, but just think stronger is positive or negative 0.7 and out, and then closer to 0, the weaker it is. All right, so we're going to use a level of significance of alpha of 0.01, right, because they told us here in the story, in order to test to see if there is a positive linear relationship between math scores and English scores for junior high school students in the city. So just based on this statement, what kind of hypothesis test are we doing? Two-tail, upper, or lower tail? It would be upper. And the clue behind that is because it says a positive linear relationship. So the positive suggests an upper tail. If it said negative linear relationship, it would be a lower tail. And if it didn't say either direction, if it just said, hey, I want to see if there's a linear relationship, then it would be two-tail. So those are the kind of clues that you'll look for. Positive, negative, or no mention at all would be a two-tail. So let's go ahead and bring all this over into the format we're used to seeing that we learned back in Chapter 9. So we'll go ahead and conduct that hypothesis test of a positive correlation. You guys already told me it's an upper. And so if it's an upper tail test, in my alternative statement, what symbol am I going to put in there? That's what we're testing for. We want to find out. Yeah, so more than, greater than, however you want to describe it. And then, of course, the null always has the equal sign in it, and then the other direction that we're not interested in. So think of it that way. Recall that our degrees of freedom is n minus 2. So I think our n, sorry, I can't remember. I think it was 52. Yeah, it's 52. So 52 minus 2, that means our degrees of freedom is going to be 50. And then our alpha is what? 0.01, right? So when I ask that, I'm just making sure we remember these concepts. The more you hear it, the more you practice it, the easier it gets, okay? So remember, the way I structure my class and also the final exam is I would kind of walk you through the same 3 steps over and over. I ask, what's the decision rule? What's the test statistic? And then make a decision based on one of our processes, whether it's the critical value approach or the p-value approach. Note that in the homework, sometimes it switches things around. Sometimes it'll ask for the test statistic first and then the decision rule. So you just want to be careful you understand conceptually what's being asked, right? So the decision rule is just what's our rejection region? What are the little tails on our curve? Whereas the test statistic, it's where we take our sample data and we convert it into something we can test, and we want to see, hey, where does it fall on my curve? And I'll hopefully if I can figure this out, do a quick visual as well. But let's go ahead and find the critical value first. So let's find that decision rule. It is upper tail test. So you're going to use this formula right here, equals t.inv parentheses 1 minus the alpha degrees of freedom. If we look at the chapter 14 Excel file, I did update it so that the first tab has all the critical values and p-values formula. This is the same sheet that you saw in chapter 9. It's the same sheet for chapter 14. It's the same sheet for chapter 10. So this is your friend for all of the chapters, 9 and up. And then on the exam, I'm going to give this same sheet as well. So you want to get really familiar with it. So you can see here critical values of t when we don't know the population standard deviation. So this was an upper tail test. This is the formula that we're using. So I just want to show you where to find it on the Excel file. But we'll go ahead and type equals t.inv parentheses 1 minus, and recall our alpha was the 0.01, comma, and the degrees of freedom is the 50. You can, if you wanted to do the 52 minus 2 and enter that in here, you can, but I think it's probably quicker just to do the mental math, but just be careful that you put in the right degrees of freedom. So it is 52 minus 2, or 50. And when you hit enter, what do we get? Fantastic, 2.4033. Let's see if I get it too. And I hope you're following along, because the more practice you get, the easier this is. 2.4033. So that's going to be our critical value here. And then for the test statistic, I'm just going to plug in my variables. So recall that R we were given was 0.84. And then we'll plug that in here along with the N of 52. So you can see it looks something like this, right? Now what I find is this is where many folks have issues depending on whether you're using a calculator or you're using Excel. It's the order of operations that can kind of throw people off. Because this denominator is got a lot of pieces to it, right? So the top's fine. You just got that R. That's going to be the last step you do. So you just leave that alone. But let's go ahead and work through this denominator. I'm going to show you how to do it in Excel. You can also try it on a calculator and see if we have the same answer. So this is how I do it. I always do it in parts. And I work it in here from an order of operations perspective. So the first thing we want to do is we want to work with the inside of the radical. So I'm going to do equals 1 minus 0.84, and then the exponent 2, because I only want it to square my R, right? So I'm going to do shift 6, that's the little caret or the little hat, and I'll type in 2 because I'm squaring it, and then I'll hit enter. That's going to give me the number right in here, and I'll go ahead and hit enter. Hopefully you get what I get. So this 0.2944, that's the number right in here. The next step is, well, I got to take that number and I need to divide it by 52 minus 2. So I can do a quick mental math, right? 52 minus 2 is 50. That'll save me some extra typing. So I'll go ahead, just zoom in a little bit more. I'll do equals. I'm going to take the box I just did and hit divide and then type in 50. So I'm just taking the number I found right above here and I'm going to divide it by 50. And then you can see the next step is I have to square root all of that. So as you can see, I'm just building and just working my way down on the Excel file. So I'll type in equals square root, so SQRT. Hopefully you're getting familiar with the square root function. We've been using it for a couple of class lessons now. Parentheses, and then I'll just click on the box I just did above. And then close parentheses and hit enter. So this right here, 0.0767 and some change, that's my denominator, right? So that's the bottom. And now I have to divide 0.84 by that denominator. So I'll just go ahead and do equals 0.84 divide by, and then all that work we just did in that radical, I'll click on it, or you can type it, whatever you prefer. And then when we hit enter, cool, 10.947. You can see I've got a lot of decimals here, so I can use my decimal mover to help me with some of that. Now, if you're using a calculator and you're rounding early, that's okay. Your numbers might be a little bit different from a rounding perspective. And I have found in these chapters that the rounding is very, very precise with MyLab. So if you're using a calculator but you're close and it says you're wrong, just send me and ask my instructor. I'll give you credit. Or use Excel and you should be good. But just kind of a heads up with the rounding. Now let's go ahead and interpret a few things. So here's our normal distribution curve. We're doing an upper tail test, right? So our critical value was the 2.4033. That test statistic was 10.9, was it 47? Something like that. Where does the test statistic fall? Where on the curve in relation to the critical value? So in relation to this line right here, and yep, it falls to the right. So it falls somewhere actually quite far out, right? It falls way out. Our t-stat falls out here, and it's okay to have a very big or very small t-stat. Just tells you like how far like in that direction it goes, right? So I'm just going to keep imagining that. So based on this, are we going to reject the null? Yes. Remember, anytime we're in the rejection region, we reject the null. Because all that's saying is our sample data, once it got converted, was so special it fell in a very, very small rejection region, or a very small tail. Let's now see what that means. We'll go back to the screen. So we rejected the null, and it can be helpful. Imagine I cross out the null. That's the top statement with the 0 in it. And if I cross out the null, that means I'm left with the alternative. So what is that saying about our relationship? Is there a positive correlation between the two tests? So the way we would describe that is because our test statistic of 10.947 is greater, right? So we're just putting it in context. Visually, you saw it was way to the right in the little tail. It is greater, right? Because the number 10.9 is bigger than our critical value of 2.4. So it's greater than. We will reject the null and can conclude there is a positive linear relationship between math and English scores. You were asked on this on exam. Let's take it one more step. Let's find the p-value. Remember the p-value, p for probability. I just want to know, what's the probability that we got this sample? So what we're going to do is we're going to take this test statistic, this 10.947, and work with it. So if we go back to our Excel file, and I'm still on this side of the formulas, right? Finding p-value for our t-values. So I also make little notes like negative t-value or positive t-value or two-tail, depending on this. We're doing an upper tail. Right, we're going to use this formula here. So you would type in equals t.dist.rt, RT for right, like the right side, upper tail test. Our t was the 10.947, comma, and then what's our degrees of freedom again? 50, yeah, we're going to go ahead and type in 50, close parentheses, and I get 0.000. Now, if your number doesn't look like that, maybe your number might be in scientific notation. So that means you have to reformat it. So if you look at the numbers format here, I always just hit that comma. That'll bring us to numbers. It's accounting form. And then you can play around with the decimals. You can see actually it's really tiny. I can keep going for a while. So yeah, many of you might have seen scientific notation. Just hit that comma and it'll fix. Now, if I was asking you to do the p-value approach, here's my p-value, 0.000. How does that compare to our alpha of 0.01? Smaller, less than, or greater than? It's less than. So if our p-value is less than alpha, what's our decision? Reject or not reject the null? Yes, we will reject. Because all that means is if I look for the area or the probability of getting this sample, it was so small, but it happened. It's like winning the lottery. The chances are so, so small, but it happened. Hence, we're going to go ahead and reject the null. And we've got enough evidence that something special is happening. We got enough evidence that we won the lottery. And so that's how hypothesis testing works for a correlation coefficient.